Okay, in the next part of my series on creating the best tournament brackets, we're going to take a look at the NCAA men's basketball tournament, but we're going to take a little different perspective on it this time. Instead of looking at it from a competition perspective and possibility of the best team advancing and things like that from a tournament setup approach, we're going to look at it more from an outcome approach. In this case, what we're going to do is look at the outcome of the tournament based on seeding. In the end, what we're going to do is we're going to look at, can we predict the team outcome based on the seed alone, or what does the seed tell us about the likely outcome for a team? Okay, so we all know the NCAA basketball tournament. Here's a bracket from, I don't know what year I pulled this off of, from many years ago. North Carolina is a champion on April 6th. So this is the way this is set up. It's a 64 team tournament. There was in this one, there looked like there was an opening round match that was a matchup between two 16 seeds, nominally is what they were, that are listed on that. You know, in recent years, they've been having the first four games typically held in Dayton for whatever purpose that is. I don't have those on there, but we'll talk about those as we go along and everything like that. So this is the usual NCAA basketball tournament. But more important to us, what matters is how this tournament gets set up. The way the NCAA tournament committee does this is that it breaks the 64 teams down, and we're only going to talk about 64 at this point. It breaks the 64 teams down into 4 different regions, and within the regions, the teams are seeded 1 through 16. We only have to think about this from a 16-team single elimination tournament within each single region. Then, of course, what can happen is that the winner of each region goes into the Final Four, and according to the way this is set up, the top seeded team in the Final Four would all be number 1 seeds, and so they're going to be all the same in that way. So we don't have to worry about seeding 1 through 64. We're only going to worry about seeds 1 through 16 within each region, and then we'll see what happens as that progresses on. So what are we going to think about? We're going to talk about this in the context of what we would call a probabilistic model of game outcomes. So let me explain to you what the basis for this is and how it works. You know, you usually think about it, hey, you know, you go to a game and the team with the most points wins and everything like that. And what does that mean in terms of relying or looking at the teams that are playing? There's a lot of different ways to view this. There's like, oh, the team was better than them on that day and everything like that. But can we get a more general type of description? And here's the way I would think about it. Well, the question we're going to ask is, what's the probability, and we'll treat it from a probability standpoint, what's the probability that Team A beats Team B in a basketball game? Well, you'd say, well, you know, the team with the most points is going to win, but is it really that way? So let's look at this case where, suppose we take a team and replicate them. We're not going to clone them because then they have to grow up. So we're just going to replicate them and have those two teams play against each other. So what I'm going to do is I'm going to take this random roster of Indiana University basketball team, and I'm going to replicate them and have them play another team made up of the exact same players of the Indiana basketball team. And I couldn't figure out how to change their uniforms to red, so I just left this as more of a sepia tone. The color photo of IU basketball team versus the sepia tone version of the IU basketball team. And you put them on the court and you ask the question, which is going to win, the left or the right team? Obviously, you can't tell the difference between them going in because they're the exact same team. And each team basically has a 50% chance of winning that game. It's a coin flip. Somebody's going to win, right? This is what the whole comes down to. In these discrete elements that we have, somebody has to win that game. The teams are perfectly equal, so they're not, but they can't tie. One of those teams has to win. Which one is going to win? The way we deal this from a mathematical perspective is we say each team has a 50% chance of winning that game. We can talk about that at an individual game level, but it makes more sense once you start talking about it as like, okay, so individual games, sure, but what if they played 100 times? If those two teams played 100 times, you would expect each team to win 50 of those times. So that's what that 50% probability means, that if they played multiple times, each team would win 50% of the times that they played. It doesn't work on a individual game, right? You can't talk about a winning percentage for a single event. We can only talk about that for the population. But we can talk about the win probability of that discrete event. Which of these teams is going to win? It's a coin flip. Literally, it's a coin flip, 50-50 chance. If I had to predict which of these teams would win, I could flip a coin and I would be right half the time. Or I could just say this team's going to win all the time, and I'd be right half the time. It's a 50% chance. Right? So that's the way what happens if we replicate the team. Now let's go to the other extreme. So let's take that same IU basketball team and let's put them up against some other competition, junior high team or middle school team or what this is. Let's have them play this team from Windsor Academy. I just found this picture online. No disrespect to the Winston Academy basketball team. I'm sure they're very good athletes and very good basketball players. And at the risk of discrediting my Purdue University Bonavides here, I'm sure that the Indiana basketball team would not have a problem beating the junior high team from Winston Academy. All right, so they're going to win. Sure they are. And in fact, it's pretty much guaranteed that they're going to win. We'll call it 100% probability or nearly 100% probability. Why nearly percent? What's the chance that the other team could win? Well, maybe there's during the game, all the members of the IU team trip over each other and all get hurt, and so they have to forfeit. That's the only chance the other team's going to have to win, right? So I can't say it's exactly 100% chance because there's always a chance that something crazy could happen that would lead to the Windsor Academy winning this game. And so there's a big difference between those two teams, and so the win probability is 100%. If we were to plot this winning percentage, here's what we could end up with, a plot that looks like this. So what we're going to do is on the x-axis here, what we're going to say is how much better are you than the other team. So the point in the middle right here is this is where the teams are equal. All right, so this is where we replicated the team and had them play against their replicates. That's this one right here, and that's where you can see that this point says that the win probability is 50% or 0.5. If you're much better than the other team out here on this end of the axis, your win probability goes up to about 100%, and so I've got that plotted out there. And if you're not near as good as the other team's much, much better than you, is the corollary of this, and so this is nearly 100% over there. That means that those same two teams from the lesser team perspective has a win probability of 0, right? That's how we can imagine the outcome of the game between this IU team right here and the other team that we bring up, either the replicate team or the team that's far less good, all right? So that plot makes a lot of sense. Now, the question that's going to end up happening is, what happens in between here and there? So what's the shape of the probability curve that's going to go between here and there? Now, make sure we're clear, because this end is the same, but the opposite of that end, whatever we have on this end is going to be mirrored over here. So we're going to have the symmetry of the system. So that's a good place to start. So we only have to think about half of it. But let's think about it from the perspective of Winston versus IU. So this is the Winston junior high team, and the probability that IU wins that game is basically 100%. So Winston's winning percentage is 0. Now, I don't know anything about going forward with the Winston Academy, like their high school, if they have a high school or varsity or something like that. But let's say this is the 7th grade team. Let's say the 9th grade team. Now, we know the 9th grade team is better than the 7th grade team. And so along our x-axis, it's going to come closer to IU along that way. But is it really going to change the win probability? You know, IU, they're not that bad this year. I don't think they'll be losing off to a 9th grade team. And so the winning percentage is still about 100. So we can put that over here as well. And maybe, you know, I would say even the high school team. You know, now the high school team's a lot better than the 9th grade team, so we still moved along this axis. But still, the probability that IU beats that team is still pretty close to 100%. So this is a 0 down here. How far along this curve do you need to go between how much better the one team is than the other? How much farther along this axis do we need to go before we start getting off that baseline of about 0? Could it be low quality Division III college team, which is certainly going to be better than most high school teams and things like that, but still IU has nearly 100% chance of winning that game. So as we keep going, there will be a point where maybe we're going to start getting off this baseline, but the probability of that team beating IU is still very, very small. Alternatively, we could look at it from the middle perspective, right? And say, what happens if we move off this center point? So when we define this center point here, this is where the teams are exactly equal because we replicated the team and therefore they are by definition 100% equal to each other with a winning probability of 50%. But what would happen if when I brought those two teams together in the safety picture, one of the starters was hurt? And therefore, the full squad of Indiana basketball is facing a non-full squad of Indiana basketball, or maybe this big guy in the middle, I don't know if he's a starter or not, but he's hurt, and so they lost a big part of that team. That means that the original team with this full roster is going to have a better team than the team without its full roster. But what's that going to mean in terms of the winning outcome? Does that mean that this team is always going to win? No, I don't think so. I mean, if they played 100 times and they didn't have one of their players, one of their starters on this team, it's going to affect them. So maybe now the better team, the team that's got the full squad, wins 55 of those games, and the other team wins 45 of those games. So clearly this team is better in the fact that it's more likely to win, but it's not 100%. It's never 100%. This is why in the NBA they play a 7-game series in the playoffs, because they know that a single game is not representative of the relative quality of the two teams. But if I did play one game, somebody's still going to win. But just because the team wins doesn't mean that they were necessarily the most likely team to win. If they played 100 times, maybe they would only win 45 of those 100. But, you know, if I have a single game, the chance that that one of those 45 games happens then is 45%, right? As I get near the middle in here, if I change it a little bit, I'll move along my axis about how much better you are than the other team, and I'll change the percentage, but I'm not going to jump straight up to here. If I move a small amount off, I'm not going to jump up to 100%. I'm going to jump off just a little bit. Ultimately, from a mathematical perspective, there are a few different ways to view this. A very useful way to view it is to use a curve that looks something like this, all right? So as the teams and start in the middle, when you're in the middle and you start moving away from there, the more you move away from how equal the teams are, the difference, there is a change in the win probability. But what happens as you get farther and farther and farther apart, it asymptotes away out toward 100 in this direction and out toward 100 in that direction. If you look right toward the middle, it's actually very linear in this region, but then it's not linear when you get out toward the edges. So this is an approach that you can use, and statistically there are some situations where this type of model is the exact type of a thing you want to do. I do a lot of work with volleyball where you have a lot of discrete elements in a volleyball game, so points are all these discrete elements, and you can get an outcome that looks very much like this type of a distribution. And in fact, it's exactly this type of a distribution as far as anyone can tell. Whether that's necessarily true in basketball or not is not clear, but I don't think the deviation from it is very, very large. So we're going to take this type of a model in order to describe the probability of winning given the difference in quality between two teams. Mathematically, what we're talking about here is just an integrated normal distribution. The great thing about using something like an integrated normal distribution is that it's the built-in functions in all your statistical programs built right into something like Excel, which I use for my calculations. And so I can use this. It's an analytical function. I don't have to use searching tables or anything like that to find it out. I can actually calculate it exactly given my input parameters. And so that's what we're going to use in this modeling. We're going to use a winning percentage as described by an integrated normal distribution. Okay, so that's the underlying model that we're talking about. Now let's talk about this in terms of real life. Okay, so that's all theoretical and hopefully based on some assumptions and things like that. Can we think about our real life outcomes in terms of probability? Well, the thing to do is to look at how often do teams play each other, and can we have a measure of how good they are, and then we can look at an outcome. So when it comes to the NCAA tournament, what we can do is we can look at seeds as a proxy for how good teams are. It's not necessarily, I understand the whole issue of how the quality of seeds and everything like that, but we can think about it in terms of at least how good the committee, using its criteria, thinks those teams are. All right, and so we're just going to give teams a numerical value on how good they are based on their seeds. And so, for example, 1 seed, 2 seeds, and things like that. The question is, does this work? And so let's look at the outcome of games between different seeds in the NCAA tournament. The easiest place to start with is with the number 1 seeds. That has the most amount of data. What I've done is I've gone back through 20 years of NCAA tournaments, and I have looked at who won the game between teams that were seeded number 1 and what their opponent was. So in those 20 years, believe it or not, there's only been 10 games in 20 years where two number 1 seeds faced each other. Now that kind of makes sense. Remember, they can't meet until the Final Four. Half of the time in the Final Four, there's 2 number 1s that actually come up meeting against each other. And by definition, when a number 1 seed meets a number 1 seed, it's a 50% outcome. There's been 31 games between a number 1 and a number 2 seed. And in fact, in those, the number 2 seeds currently in the last 20 years have an edge, 16-15. It's not overwhelming or anything like that, and we wouldn't expect it to be overwhelming in either direction, but in fact right now it's actually the number 2 seeds are up by 1 in the head-to-head number 1s versus number 2, so it's 48% there. After that, now it starts making a little bit more sense. So 22 games between number 1 and number 3, number 1 seed wins 2/3 of the time. 1 versus 4, it's winning 3/4 of the time. 1 versus 5, a little more than 3/4 of the time. Interestingly, there's only been 3 games in the last 20 years where a number 1 seed has faced a number 6 seed. Number 1 seeds have won all of those. 1 versus 7, number 1 is 4-1. 1 versus 8, now you're up to 80% winning percentage for the number 1 team. 1 versus 9, 89%. Which is what you'd expect because 8 is better than 9. And then the only other, so there's 1 versus 10, 1 versus 11, 1 versus 12. There's just a handful of games along there. No 1s versus 14s, no 1s versus 15s. There's almost no way for that to happen. 1 versus 15 can't happen until the regional final. So you don't see those. Those are on the opposite sides of the bracket. 1 versus 16, of course, is where it starts. The big news is whenever there's a 16 that beats a 1, that's a huge upset. But over the 20 years, it's 78-2 is the record of the number 1 seed against the number 16 seed. What I've done in terms of percentages, I've only looked at those matchups where there's at least 10 head-to-head matchups, and so I'm not going to use the 5 games between 1 and 7 or the 12 games or 9 games between 1 and 12. Just not enough to actually be legitimate. In fact, even the matchups with 10 are kind of dicey and can lead to bigger outliers along the way. All right. But so here's the winning percentages for the outcomes. It goes like for 1 seeds against the other seeds in the tournament. Now the question is, how does this match up with our discussion on the previous slide about the integrated normal distribution function or anything like that? If I scale things right, And I can put these percentages on the plot that I had before. And when I do that, this is what I get. And you can see, in fact, it looks really, really good. This line is fitting these data exceptionally well. I really think it does. I mean, you couldn't, given the scatter in the data, given the number, the small numbers, relatively small numbers of data that we have, data points, this is a remarkably good fit to the data, right? So here's a 1 versus 16 team seed. Here's the 1 versus the Winston Academy team over here. So you can see, yeah, there's a huge difference between these two, but not very much difference in the win probability, and that makes a lot of sense according to this integrated normal distribution. Yeah, this type of description that I'm imposing on the win probabilities and assuming for the win probabilities of one seed versus another looks to be a reasonable model of the distribution of the winning percentages for the teams in the NCAA tournament. The great thing is I can look at 20 years of data and I can do this same type of analysis for every permutation along the way. So here's my number 1 seeds versus all the other seeds. So we're going to go down the column here. 1s versus all of those, 2s versus everybody, 3s, and so 2 versus 1 right now they're at 51.6%, which is 1 minus that. So along the diagonal, you all have 0.5, so that's a 50% because it's 1 versus 1, 2 versus 2. There's a 50% along the diagonal. And so you can look at whatever seed you want, say the 5th seed versus a number 4 seed. There's another one where it's inverted a little bit instead of so 5 seeds currently have the edge on the 4 seeds in the total outcome. 5 versus 12 currently has a winning percentage of 620. 5 versus 9 or 5 versus 13, that's 9 out of 10. So this is a little bit off the line. I can look at all these different permutations here and combinations along the way. The thing I'll remind you of, the only data I'm putting on here where there has been at least 10 games between 2 seeds. And so there's not been, in 4 versus 8, there's not been enough games, 4 versus 8, to actually indicate any more reliable data. With these data points, what I've done then is gone and used this integrated normal distribution model to try to create a global surface of probabilities to basically fill in the blanks. And so I'm going to try to fit, these are the data points what I'm going to use to fit the curve that covers the whole graph. That way I can fill in those probabilities for the positions where we don't have enough experimental data. So I'm going to try to put an analytical model onto this. After I do that fit, this is what I end up getting. Now this is a fit to the global probabilities, and so you can see, you're going to see some things that you have in features here. So 0.5 along the diagonal, that's what you should have. What you also have is, look at the extremes, so 1 versus 16, you can see that the probability of 1 beating 16 according to this fit, we'll talk more about that later, is about 95%. It's a little bit off of the real data, which is more like 97.5, but there's variation along the way. I'm trying to get a best overall fit to the data that I showed you on the slide before. And so some are going to be high, some are going to be low, and so there's going to be some deviation along the way, but this is the fit that gives the minimal deviation for that data on the previous slide. Okay. The great thing about this is now I have this analytical function, and this is based on an integrated normal distribution. So I have an analytical function that describes the probability based on the difference between the seeds. And so if there's no difference between the seeds, I get a 50% probability. You can see, and this is the way the system worked out, the 1 point difference in the seed leads to basically a 54% probability of winning for the higher seeded team. And that works whether it's 1 versus 2 or 2 versus 3 or 3 versus 4, et cetera, et cetera, et cetera. And so you can see these commonalities along the diagonal lines. And that's just the way the nature of how that comes out. A difference of the seeding position of 1 leads to this amount of change in the probability outcome. All right, so that's my initial attempt at creating this global surface. Great thing about this is that we can use this now to estimate win probabilities for games between teams where we don't have enough data, right? What did I say before? We had said we had a 4 versus 8. There wasn't enough data in there, but now based on this analytical fit, we can estimate that that should be a winning percentage of about 662 for the number 4 seed. So the number 4 seed should be winning, have a win probability of 0.66. You can do this for any of these types of things, right? 9 versus, what are we going to say? 9 versus 12, which I'm sure didn't match up at all. So 9 has a 62% chance of winning, and 13 versus 16, who they would never face, another 62%. I'm still on that diagonal. So I can use this analytical model to estimate the win probability for a game between 2 teams if I know their seeds. Okay, so now given these matchup probabilities, we can use them to calculate the probability that a given seed will advance through the NCAA tournament. So for example, here's the brackets in one of the regionals. You have the number 1 seed versus the number 16 seed. If we use the probabilities that are on the previous slide, we see that the probability of the number 1 seed beating the number 16 seed is something like 94%. Conversely, we could turn that around and say that the probability of the 16 seed beating the 1 seed is about 6%, right? But we can do this with all these different matchups in the bracket. So an 8 versus 9, there's a 54% probability that the number 8 seed wins that game. 5 versus 12 is a 77%, 4 versus 13, 83%, et cetera, et cetera, et cetera. So we can use those probabilities from that analytical model that we're using. Cool. Then what we can do is, once we have these probabilities for advancing out of the first round, we can look at the probability that a team advances out of the second round, and that's going to be making the Sweet 16. So using the probabilities that we have here, we can calculate the probability of the number 1 seed advancing to the Sweet 16 is about 82%. Now this is the probability before the tournament starts of the number 1 seed advancing to the Sweet 16. It's not the probability of the number 1 seed making the Sweet 16 if they win the first round. It's before the tournament starts. This is what we would say for the probability of the number 1 seed making the Sweet 16 is 82%. By using that same type of an approach, the probability of the number 2 seed making the Sweet 16 is something like 60%. Interestingly, the probability of the number 4 seed making the Sweet 16 is only about 46%, even though the number 4 seed is the most likely seed to come out of this quadrant in order to make the Sweet 16. The chance of them doing it is only like 45 or 46%, so a little under 50-50. So what that's saying is basically half of the number 4 seeds don't make it into the Sweet 16. We can take this a step farther. What is the probability that they win their first round in the Sweet 16 to make it to the final 8? And the number 1 seed probability is 60%. The number 2 seed has a probability of 36%. That counts for what, 97% of the chance of getting there, and the rest of that is summed up among the other seeds. The probability that the number 1 seed gets to the final 4 looks to be about 43%. So 43% of the number 1 seeds make it into the final 4, less than half of the number 1 seeds will get into the final 4. The probability of the number 1 seed, of a number 1 seed getting into the championship game looks to be about 25%. And then you can look at even the chance of the number 1 seed of winning the overall tournament. And so this column here shows us the championship probability based on the actual seeds. What this means is that if your team is seeded number 1, there's a 15% chance that your team will win the national championship. It drops off very quickly as you go down to lower seeds. Number two, it's down to 3%, and number three seed, there's only 2% chance, and it drops off very quickly. The chance of a 16 seed winning is very, very small. And in fact, that's very much what we've seen. Just to let you know, over the last 20 years, there's been 80 number one seeds, and in those 20 years, 13 of those championships have been won by one of those number one seeds. And so that's a little bit more than 15%. It's more on the order of 16 or 17%, but it's still very close to what's being expected. In fact, we can compare the outcomes of the national championships to what we predict based on this probability model that I've had. So this 15% probability that I said for number one seed winning the national championship, given that we would expect to have seen 12 number one seeds win the national championship in 20 years, actually it's been 13. So we're right very close to what has been observed. The probability for number two, we'd expect to have 3 wins. There's only been 2. Number 3 seeds, we'd expect 2 wins. There's been 3. And then it gets smaller as you go up. Interestingly, if you look at this expected wins column here, it only sums up to 19. And that's because these probabilities get too small. So if I actually take and bin up the probabilities for the seeds 6 or higher, the agreement with the actual results gets even better. We still expect 12 wins for the number 1 seed, 13, 3, 2, 1 for a number 4 seed. 5 seed, we should have expected at least 1 5 seed to win so far. Nobody's done that. 6 or more. In fact, based on just simple probabilities, we would have expected 1 team seeded 6th or higher to win the national championship over these 20 years. And sure enough, that's exactly what happened. What was that? Connecticut was a 7 seed, and they actually won. So in the end, what I'd argue is that if you look at our predicted expected wins in terms of national championships versus the actual outcomes, in fact, this probability model works extremely well. We have a really good reproduction of the outcomes that we've observed, and we've predicted it just using these simple probabilities. Now we have to think about this in terms of advancing and all seeds. There's a number issue in coming up here. First of all, you'll see that this round 1 value doesn't quite match up what I showed you on the previous slide. And there's an important reason for that. It goes back to our integrated normal distribution function. You know, I showed you that plot that showed that, hey, that the distribution function was a really good fit to the actual outcomes for 1 seeds versus everyone else. And that was true. The thing I didn't show you is what would happen if I put number 2 versus everyone else on that. The problem is, it's not that an integrated normal distribution function wouldn't fit the data. It's that the scaling along the x-axis wouldn't be the same. The question is, how steep is that curve rising as you go from, from how much better you are than the other team as you rise up there? How steep does that rise occur? What I found in my modeling is that while most of them work pretty well, 2 through 15 are fine, the scaling for the 1 seeds and the 16 seeds isn't the same as those other seeds. Okay, so the difference between a 1 and a 2 seed is not the same as the difference between a 2 and a 3 seed. That's kind of what I'm saying here. And the same way, the difference between the 14 and 15 seed is not the same as the difference between a 15 and a 16. So what I've done in my model is I've actually pulled those out a little bit. The 1 seed I've separated off a little bit. The difference between the 1 and 2 seed is more like the difference between 2 and 6. So that's more what the difference is going to be. 16 seeds, on the other hand, are a whole different ballgame. The difference between 15 and 16 is nowhere near the difference between 14 and 15. The difference between 15 and 16 would be like more like the difference between 15 and some team seeded 60th, right? And it's because of automatic qualifiers that come into the tournament, that the automatic qualifiers are not necessarily in the next group of the best teams that are available. And so you can have teams in the tournament that might be the 250th best team in the country, but they won their conference tournament. There's going to be another one that's the 190th best team in the country and the 160th best team in the country, and those are all going to be 16 seeds, whereas the 15 seeds are more likely to be in that top 60 or something like that. And if you look at it from the distribution of teams, everything's pretty good, but there seems to be a really long extended tail on the low side at the 1 seeds and then way out there in the 16 seeds. And that's not unexpected, especially at the 16 seeds. We knew that was going to be a problem, that 16 seeds are a different kettle of fish here. The fact that the 1 seeds are so different from the 2 seeds is something that was a surprise to me. But in terms of modeling the data, that's what I needed to do in order to get that good agreement with the outcome. If I didn't do that, I only predicted something like 9 number 1 seeds to be winning the national championship. That clearly isn't going to be right. I had to give one an advantage in the probability, and that gives me the answer that we'd hope to see. All right. So round 2, when this is the probability of making it to the Sweet 16, in the end, this is the table that you want to refer to look at your probability of your team advancing in the tournament given its seed in the tournament. We've already talked about advancing out of round 1, advancing out of round 2. This is the probability that your team makes it to the Sweet 16, an 80% chance that a number 1 seed makes a Sweet 16. The 14 seed, which is always one of those big first round upsets, has a 5% chance of advancing into the Sweet 16, so basically 1 out of 20. And you can look at all the other probabilities in between. Of course, the 2nd seed has the best chance of making it, 60%, 3rd seed 53, 4th 46, etc., etc., etc. Winning round 3 gets you into the Elite 8. Winning round 4, that's your probability of making the Final 4. And so you can see that number 1 seed has a 43% chance of making the Final 4. Number 2 seed, something like 17%, or 1 out of 6. Number 3 seed, 12.5%, or something like 1 out of 8. So that means every other year we should expect a number 3 seed to be in the Final 4, and then the probability drops off as you go down, 1 out of 12, 1 out of 16, etc., etc., etc. Round 5 is your probability of making the championship game, and then round 6 is your probability of winning the championship. These probabilities are all based on a 64-team tournament, so the teams are all seeded in the 1 through 64 spots at the beginning. If you are one of those teams playing in one of the first 4 games, what you need to do is cut your probabilities in half at each point, because you have a 50-50 chance of getting out of that first round. For example, there are often number 13 seeds that are matched up in one of these first 4 games, and the probability of that any one of those teams gets out of there is 50%. That means the probability of one of those number 13 seeds making it out of round 1 is only 11%, and the probability of making it to the Sweet 16 is only 3.5%. That's because we can't tell which of the number 13 seeds is going to come on. So it's a 50-50 chance for either one of those number 13 seeds. Remember, these probabilities are for your team before the tournament starts. If you are a number 13 seed in one of the first 4 games and you win your first 4 game, then your probability jumps to the 22.5% that you see here. Hey, if your team gets a number 7 seed this year, you can see you've got a 60% chance of advancing out of the first round, 24% chance of making the Sweet 16, 10% chance of making the Elite 8, 1 in 30 chance of making the Final 4 if you're a number 7 seed. How about that? We can do the same analysis we did before and look at the expected versus actual results. And so for all these different rounds. And so winning round two, remember, this is the round you have to win to get to the Sweet 16. And by this model, we predict that 65 one seeds should have made the Sweet 16 over those 20 years. And in fact, the answer is 66. Hey, we pretty much got that right. That's really good. And you can look down through, there's a lot of numbers here, and it's not worth squinting at them too hard. And the easiest thing to do is just look at the deviations. And so what I'm going to do is look at the deviations from the expected outcome. And so what I'm going to do is say, how many teams were actually advanced to this point versus how many teams expected. Win round two. So how many teams got to the Sweet 16 versus how many we expected them to, and we can do that for every round along the way. And believe it or not, if you look at this, in fact, it's remarkably good. That's what I think. Literally, or half of the values in here are zeros, which means that the model exactly correctly predicted how many teams should be in each of these different spots. Now, to be fair, it's not hard to predict that no 16 seeds are going to make the Sweet 16 or out to the championship. But still, so half of the possibilities are exactly right. Of the 40 that aren't right, half of them are off only by one win or loss. So in fact, it's actually doing a really, really good job of reproducing these results that have been observed in the NCAA tournament. So this model is based on looking at outcomes, but it's using those outcomes, turning them into probabilities, then using the probabilities to predict how many teams are there, and then we look to see how many teams are actually there. And you can see that it's coming out in a reasonable way. Now, there are some deviations in here, and so, for example, you can look up here in terms of how often teams win round six, and the number one seeds here have a -6 on that. What that means is that the actual number of number one seeds that win round four in order to make the Sweet 16 is actually lower than the expected value by 6. And if you think about that, how big that is, and I don't remember how many there was, there's something like 36 or something. So there is actually a fairly big deviation of that. So number one seeds have significantly underperformed, not when it comes to getting to the Sweet 16 in the 3 rounds, but when it comes to that regional championship game, you're seeing number one seeds underperforming compared to what they expect. On the other hand, the ones that do get into the Final Four are succeeding very well because we've got the right number of teams that are going to championship games, the right number of teams winning championship games. But there's a big stumble here in the regional champions to get to the Final Four. A couple other things worth noting. Another place where we see a lot of deviations, 14 seeds in round 2 is at -4. Point out 13 seeds in round 2, -3. These are seeds that are underperforming, getting to where they're supposed to be. And the reason I like this is because if you look at what this is we're talking 13 and 14 seeds winning round 2. So we're talking 13 and 14 seeds advancing or into the Sweet 16. So 13 and 14 seeds aren't advancing into the Sweet 16 at the level we would expect given this competition model. You want to see somebody that's really underperforming, look at the 6 seeds. This is where there's a big problem. 6 seeds are doing a terrible job, relatively, getting into the Sweet 16. This is carrying forward that their lack of teams in the Sweet 16 means that they're going to be underperforming when they get to the Elite 8 and into the Final Four. So they're way underperforming there. So it's the 6 seeds that are doing far worse than expected all the way across the board. At least with the number 13s and 14s, they're moving on as expected. Well, that's because they're expected to lose, and so that's not a big deal there. And so they're moving on to the next round, and everything evens out at that point. We could take it the other way. Who are the teams that are overperforming? How about number 2 seeds? Number 2 seeds are overperforming, significantly overperforming when it comes to round 3 and round 4. So this is winning at the Sweet 16, so advancing to the Elite 8. This is winning in the Elite 8 to advance to the Final 4. So the number 2 seeds are overperforming when it gets into the Sweet 16, that they are overrepresented when it comes into the Final 4. So number 2 seeds historically have overperformed their expectations at the regional level. They're not overperforming their expectations and getting into the Sweet 16, but once they get there, that's where they are overperforming significantly. And the other one is the number 11 seeds, right? This is coming at the expense of the number 6 seeds. But yeah, and this is where it comes into the Sweet 16. So number 11 seeds are the big ones that overperform in that second round, unexpectedly making it onto the second round. And then they carry that through as this progresses. And I don't know if you remember back to the early slide, the one thing we saw that it was the number 11 seeds are the ones that give number 1 biggest challenge. I think they're 3-3 against number 1 seeds, which is way, way, way closer than should be expected, right? It should be 5-1. But no, there's been a couple big upsets for the 11 over 1. And so that's led to a big overrepresentation of 11 seeds when it comes into the Sweet 16 and beyond, right? I want to go back to this one just a little bit. This 13 and 14 being underrepresented in the Sweet 16. You know, you often hear this talk, and make no mistake about it, when the 13s and the 14s win those first round upsets. Being an alum from University of Northern Iowa, I can say an awful lot about that because it was Mo Newby's shot at the buzzer in 1990 when number 14 seed UNI beat number 3 seed Missouri when I was a senior in college. And so you get all this talk, and you know, the media will tell you, it's like, hey, remember, you know, the first 2 weekends is all about the small schools, but the next weekend is, Sweet 16 is about the big schools and everything like that. You know, it's not actually borne out by the data. And in fact, it's borne out the other direction. What we've seen over these 20 years is that there actually has not been as many upsets of 13 over 4 and 14 over 3 as we would expect based on this competition model that I've created. In fact, statistically, we should have seen more of the 14 over 3s and the 13 over 4s. We should have seen more of those upsets along the way. So not necessarily the time for the little guys. The little guys that really do show up in the first week are, of course, in the first weekend are the 11 seeds, right? The 11 seeds and 12 seeds, on the other hand, have been doing that. So the 12 seeds are a little bit overrepresented. The 11 seeds are sensibly overrepresented. 7-10's not been a big thing for that. And so it's not the little guys, the 13s and the 14s. The first weekend is really about the 12s and the 11s. That's where they're the ones making the noise and going on from there. And then we've seen already that when it comes into the second, into the Sweet 16, it's the 2 seeds that are the ones that really step up. 1 seeds, yeah, okay, in the first round, but they really fall off when it comes to regional championships. And so it's not necessarily the big guys in that it's 1s and 2 seeds, but the 2 seeds are the ones that really take over when it comes to the regionals and over exceeding their expectations. Future Paul here, I always wanted to say that. We need to be careful when we think about how much over exceeding expectations we're talking about here. This is 5 extra wins in the course of 20 years. And so that means we're talking 1 extra number 2 seed making the regional final or the Sweet 16 every 4 or 5 years. That's the level of over exceeding expectations that we're talking about. That's how good this model really is. Once every 4 or 5 years, we see a team win that we didn't expect to win in that time, at least according to the overall probability. That's not a huge over expectation. It's not like number 2s are winning all the time. It's it's happening a lot more than expected, which means once every 4 to 5 years. And of course, there's always that 11 seed. Boy, those are crazy, right? When you see those 11 seeds come through, um, acting very out of your normal expectation. Okay, so what do we learn from all this? Actually, it really is possible to model the outcomes in the NCAA men's basketball tournament by considering the win probability based on seeds. Knowing nothing else but how your team's seeded, you can actually have an idea of how likely that team is to advance in the tournament. Now, obviously, this doesn't do much good when you're putting your brackets together because all it is best seeded team is most likely to advance and everything like that. But we can look at the grand scope of who all is going to make it to whatever position and everything like that. The other thing is that you can take the same type of model once the teams are put into place and you know what teams are there, you can do a little bit better than this because you can use, instead of using just generic seeding values, you can use more precise information coming from things like Sagarin rankings or KenPom or whatever you want to use. You can actually create this better type of competitive model that is a more precise indicator of outcome probability than what I've had here. That breaks it down. Instead of having it on a 16 team basis, now you've got a 64 team basis, and so you have more precise probabilities that you can write for those systems. But in the end, once you do that, if you had more precise probabilities, you could even do better. But the whole concept works, so you can really model these outcomes really well. The one thing to remember, what we're talking about modeling outcomes is we're modeling populations, and just like you can't use probability to describe a single game outcome, you can only talk about probabilities over populations. Same thing happens in terms of modeling the outcomes of the basketball tournament. This is why I'm looking at it over a 20-year data set. And I stopped at 20 just because I got tired of pulling data off the web. But it's 20 years worth of data that I'm looking at the conglomeration of that and looking at the patterns that emerge. But the wild thing is that the model that I've been able to create out of this, which is a statistical model based on probability, is doing a really good job of reflecting the distribution of winners over those last 20 years. It really is. And so, you can say, oh, UConn did a great job when they were the number 7 team, and how wonderful it is that they beat the number one seed or won the national championship. Does that prove that UConn was suddenly better during the tournament, or does it just prove that the probabilities worked out that UConn was able to succeed and win those games where they had a low probability of winning, but they won anyway, right? There's over 20 years, there's a 5% chance that a team seeded 6th or lower is going to win the NCAA tournament. And we've seen that. That's exactly what happens. When you look at the outcome and where the model falls off and things like that, you can use this model to see some patterns. Number 2 and 11 seeds are overrepresented in the Sweet 16, and moving on to the Final Four, 1 and 6 seeds end up being underrepresented, especially when you get to the Final Four part. It's the number 1 seed, and 6 seeds actually just, what is it? Is it 6 seeds are underperforming, or is it the 11 seeds are overperforming? I don't know what the answer is, but the 6 and 11 matchup is the most intriguing one that you actually see in the NCAA tournament over the years. It has been for 20 years. So that's a way that, now that we understand the concept of tournaments and everything like that, this is another caveat adding on to our conclusions. Over the previous analysis we've always said, assume that the better team always wins. Now we can see what happens if we don't assume that the better team always wins, but that the better team has a probability of winning. What impact does that have on the outcome of a tournament? You can see that it's pretty significant. If anybody else has any ideas of something else I should take a look at, be sure to leave a comment. And if you like what I'm doing, do the YouTube stuff, leave a like. Add a comment for me. I'm always trying to think about what I should be looking at next, and so let me know what you want me to do. All right?